right, now we've just completed the titration section, and we're now at a point where the school year is coming to a close. Never thought we'd see this point. It seemed like forever to get here, but now that it's here, we're going, wow, where did the time go? So we're running out of time, which means that I have X amount of material in Y amount of time, and unfortunately X is much greater than Y. So that means then that I'm going to have to eliminate some material, including an entire chapter. So I'm melding this whole group into what is shown on Google Classroom as miscellaneous. So I'm kind of taking little bits of chapters out that we normally get through under a normal school year. So this actually comes from the next chapter, chapter 18 in your textbook, but we're only doing like a couple of sections from that, and then we're going to move on to something else. This is called insoluble salts. Now, what that means is, first of all, the word salt means that you're dealing with an ionic compound, whether it's an inorganic ionic compound or an organic ionic compound, and we'll talk about both of those as we get through it. But they're not very dissimilar from the acids and bases that we just talked about. So let's talk about that and see the chemical equations that we write to represent them. When we have a strong acid, we said we can identify the fact that it is a strong acid in terms of equations by using a single arrow. So if we use hydrobromic acid, which dissolves completely in water. So we use aqueous for this. And honestly, we've never really said this before, but in order for an acid to be considered an acid, it has to be an aqueous solution. Hydrogen bromide is a gas until it's dissolved in water, and then it becomes an acid. So just a little tidbit to throw out to you there. But the fact that this is a strong acid, and the fact that strong means 100% dissociation, breaks down completely, we use a single arrow to show that. Now the products are not any different from a weak acid in that we get the same basic substances, a hydrogen ion or a hydronium ion, depending on which approach you want to take, and then the remaining particle or particles will have a negative charge and will be aqueous as well. This is what we use to represent that. Now, there are certain compounds or certain salts that are completely 100% soluble in water. And so it will be represented very similarly to this. And what we generally use as a guide for you to figure that out is that you have to have group 1 metal ions, or 1A metal ions. And the one we generally deal with are the top 4, the lithium, the sodium, the potassium, and the rubidium. You get past that, it's getting pretty obscure. Or cesium, I'm sorry, not rubidium. But also, it turns out that ammonium falls in that category as well. Now, ammonium is ammonia with an extra proton attached to it, so that's NH4 positive, where ammonia is NH3. But this is an ion that, if you have that in your ionic compound, is 100% soluble. So those are the positive ions. The negative ions that are always 100% soluble are the what we call the nitrogen compounds, NO3 negative and NO2 negative. We have the chlorine ions, polyatomic ions, ClO4, ClO3, ClO2, and ClO negative. This is perchlorate, this is chlorate, this is chlorite, and this is hypochlorite. that works pretty well for the or the inorganic compounds. There might be a handful of others I've mentioned in the script, so follow that. But there are also some organic ones. And the organic ones, now, of course, organic meaning carbon and hydrogen-based compounds. You're going to find the formate ion, or the methanoate ion, which is HCOO negative, and CH3COO negative, which is the acetate or ethanoate ions, and on and on. Those tend to be completely soluble in water up to about 6 carbons. And then so these are based upon acids that's lost the hydrogen, and that's why they have the negative charge. Now the bases that gain the hydrogen, that are kind of counter to these, would be like, we talked about ammonium already, but there's also, to make it completely organic, you gotta have carbon and hydrogen. So we have, now this is methylamine if I put a 2 there, but if I add a proton, that's called the methylammonium ion, and that is always 100% soluble in water, generally with a chloride or bromide or fluoride. Now they are not, those three, those halogens, or what we call the halides, are not in that list up there because in inorganic compounds they are not always soluble in water. A good portion are, but a good portion are not. But if you include it with these ions right here, you will find that they will be 100% soluble in water. You can have ethylamine, and then add a proton to that, and that becomes ethyl ammonium. Ammonium. And anything out of that chart on page 736, you add a proton to it, that'll be the conjugate acid to each of those bases, and they tend to all be soluble in water, except for maybe possibly the benzene ones. I'm not 100% sure of that. So, if you're trying to figure out if you have an ion that is 100% soluble in water, this is a good guide to go by. All right? So, let's take an example. Let's suppose that we have the compound PB3ASO4. And we want to write a dissolving reaction or dissociation reaction for this. So the question is it in that list of, is either of these ions in that list of ions that I gave you? Well, if you go back and check that out, the answer is no. You don't see lead in there anywhere. You don't see arsenate anyplace. So we can safely say probably it's going to be insoluble. But let's talk about the insoluble salts now before we get back to that example. How do we know with 100% certainty, or let's say 95% certainty, not 100%, but 95% certainty that we have a salt that is insoluble? Well, it turns out in this chapter, and in the appendix, there's a list of insoluble salts. And it's on pages 772 and 773, and appendix A18 and A19. There's a big honking list of compounds that are considered insoluble. I'm going to spend some more time in the next lesson dealing with what all that means and how we can make certain predictions based upon that. But if they're on this list, then you know with great certainty that you're dealing with an insoluble salt, or as what they also call a partially soluble salt. So how do you represent that? Well, it's going to be analogous to the weak acid. Now let's try to remember what weak acids do. Let's take hydrofluoric acid. hydrofluoric acid is HF. This is not one of the 7 strong acids I gave you. And so what we use instead of a single arrow, of course, is going to be a double arrow, to show that not all this breaks down. In fact, a very small percentage, in the neighborhood of probably between 1 and 5%. I'd have to do the calculations of it. Let's talk about that too later on. But the products are the same. H positive aqueous plus F negative aqueous. Now, I say products because this is the result of the partial breakdown, but in the beaker itself, when we did the acid up here, the hydrobromic acid, in your beaker, you will not find any HBr in there. Or if you do, it's one of the extremely small number. There is a slight, ever so slight number of HBr that will remain together, but for all practical purposes, 100% actually breaks down.